All right, so it's time to do some coding. So right now what I did was I opened up RStudio, and you can see right now it's kind of blank. Yours might look a little bit different if you've been playing around in it. Maybe you've opened up a .r file, maybe you've opened up a .r file session or an R notebook, who knows. Right now this is what it kind of looks like when you just installed it and haven't really done anything with it. So what you see right here in the left-hand side says console. This is very similar to if I were to start R in the command prompt like this. It's basically just giving you a way of interfacing with R. And that's about it. I'm going to exit out of the command prompt, come back over here to RStudio. So I've got this console. I could type commands right in here. I could do something like, make an array of numbers that look like that. I could say, hey, spit out that array, and there it is. So what I did was I have X here. X is the object that I'm creating. Then there's this funny arrow thing. And the way you type that arrow is you're going to create the less than sign and then a minus sign, and that creates the arrow. I'm told a long time ago there was actually keyboards built to do that because R is based in part on another language called, I believe it was Lisp. And Lisp used these arrow functions as what we call assignment operators. So what's happening is when I type out this command right here that I just highlighted, so X, and then I'm going to assign something to it, what I'm saying is I'm telling the computer, create an object called X. And we're going to put some data type into that object. And like I said, here I'm creating technically it's a vector, right? So I'm creating a vector of numbers. You don't get too hung up in the terminology of things, especially when you're first starting, because it's extremely overwhelming. Just know that if I need to create a sequence of numbers and I know what they are ahead of time, I could just do something like this. And C, you can think of that as kind of concatenate. And if I want to see what X looks like, I just type X and enter, and I can see that I got the value 0, 1, 2, 3. So this would be useful for things like maybe you needed to do some kind of multiplication. So like if you wanted to take 2 times those numbers, you could type 2 times X. And that times that I'm using here is the asterisk. So 2 times X, and you can see now I get 0, 2, 4, 6. So it's literally, for those of you who have had linear algebra, all we're doing is we're just doing simple vector multiplication. So we're taking the number 2 times the vector, and then this is what we get out of it. So this isn't, it's nothing too terribly difficult to get a handle on. I could also just do something like this. If I wanted X to be just a single value, I could do that. So that's really what you get from the assignment operator. Assignment operator is kind of fun. So one of the things I should probably tell you about is an object type called data frames. So that's a data.frame. And data frames is one of the more primitive objects to hold things like tables. And you'll see more examples with data frames as we go along. But if you start doing some reading on R and people are bringing in huge tables of numbers and stuff that they want to analyze, 9 times out of 10, it's probably going to be a data frame because that's what most of us old R users have been using for a long time. There's another newer, fancier object. I believe it's called Big Table. Some people use that too. You're not going to see that as often because it's not one of the R primitives. And most of us old folks who've been using R for a very long time, we tend to stick with the primitives because they tend to work very well with very little memory overhead. So anyway, that's kind of that's the most important syntax that you're going to have in R. And like we'll go through more syntax as we do more complicated things, but really this assignment operator, this whole arrow thing, is probably one of the absolute most important things that you're going to deal with. Now then, if I wanted to create a record of what I'm doing, I could go up here and I could choose a couple different things. I could do an R script. So an R script is useful if I'm just experimenting and I don't necessarily want to use the console because I want to keep a history of what it is that I'm doing. I'll do things in the R script. And so The way I get things to work in the R script is I can write a bunch of things. So 1, 2, boop, 3, okay? And then I can say, all right, and then I want 2 times x, and let's save that. Let's assign that to y, okay? And what I can do is now, if I want to run this, I can just be up on the first line, and I can hit run, and you can see, oh, there it is, right down there in the console, popped up. And then you can see that when I hit run, it automatically moved the cursor down to the second line, so I could hit run again and do that. Now, the other thing you could do is you could just highlight all that you want to run, then press Control and Enter. It does the same thing. You could also highlight what you want to run and press Run, and it runs everything. So there's other fancy things you can do. I can't remember quite what this does anymore. It's kind of a new thing. Ooh, source the contents of the active document. Neat. So that's not a big deal. If I want to save it, I can save it. I press Control S and I can save it in my directory. That's basically how we use this. So if I'm going to try to do some things rather complicated and I just want to write some code and I want to try out some new ideas, I'll usually do it in a .r file. And then if I wanted to save it, like I said, I do Control S and I can try to save it someplace. I could also hit this little save button here and that'll do the same thing. The other thing that's really neat, and this is one of the reasons why I like using RStudio, is because over here under environment, it has my 2 objects that I just created. It has object X and object Y, and it gives me a hint as to what they are, or it tells me exactly what they are if it's one of these smaller primitives like a vector. It tells me there's a 4-element vector. The values for X are 0, 1, 2, 3. And it tells me that Y is also a numeric vector with 4 elements, 0, 2, 4, 6. Which is pretty nice. You also have this history. This history tells you exactly what you've been doing lately. So you can even see some of the stuff going clear back to, I don't know, when I was using this probably a couple weeks ago or something. So you get to see all that stuff too. There evidently is a tutorial. I've never used it, but that sounds pretty cool. I forget what connections is. I don't use it, so I don't remember what it is. The other part of RStudio that's fun is you can look at all your files within a directory. If I wanted to, I could create a project. So we can do a new project. And then a project just goes into a directory and then it helps group things together. So that's what's nice about this. So I had a project open earlier that was within this. And so, in fact, there it is. That's the R project file right there. But you can see I've got lots of different files I could pull up from here. Like I could do, let's see here, this one right here. And this is one of the things I have on my other screen. And this is just an R notebook. And what's nice about R notebooks is we can use these to write reports for us. And we use special syntax. So for instance, in this R report, it's using what's called Markdown. You can look that up. It's M-A-R-K-D-O-W-N, Markdown. And so one was a hash symbol, put a space, and then here I write background. That represents a level 1 header. This 2 hashes represents a level 2 header. And so the background, you can see the background of this, it's basically somebody ran a test and they want to know if they are pregnant or if they have cancer, and that's the medical diagnostic testing example that it feels like we obligatorily always do in these types of courses. Here, if I want to show an equation that is in pretty form, I have to write it in the LaTeX form. And so that's, some people say latex, L-A-T-E-X. It's not pronounced latex, it's pronounced LaTeX. It just kind of gives me a chuckle every time I see it because I always think, oh, latex. No, it's LaTeX. And in order to get it to print properly nowadays, we do $2 to surround our LaTeX formatted equation. And so we can see that for the most part, you just write everything the way you normally would see it, like right here. And then the equal sign is that equal sign. But then for a fraction, we use a special syntax, and that is \frac. And then we use curly braces. So the first set of curly braces, the stuff that's in those, is the numerator. And then the stuff that's in the second set of curly braces is the denominator. And so that's how we can get pretty equations in here. So you can see I can write, all kinds of text, blah, 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 blah. I like to write a lot. I like to say a lot of things, blah, 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 blah. And then we got here these 3 tick marks, and then the R in the curly braces means that this is going to be our code. And I don't mean our code, I mean our code. So code for R. Okay? I sound like a pirate. R. And what's going to happen is between these 3 ticks, from these 3 ticks to these 3 ticks, everything else in between is going to be R code. And so now you can see I've got some R code and I've got a bunch of explanation going on here. One of the nice things I can do is I can go to knit and I can say, hey, make this an HTML file. And it's going to say, you need to get this other package, blah, blah, blah. So we're going to let it go get the other package. I literally just installed this RStudio not that long ago, so I don't have all my normal packages installed for it yet. But you can see then it makes this really pretty HTML file. So this is what a level 1 looks like. This is what a level 2 header looks like. I don't think I have any level 3s. Nope, I don't. And then you can see how the equations format within this HTML file. It's actually really cool. Okay. So then you can also see how we've got this code, and then what happens here? We get the output of the code. So that's pretty cool, right? So here you don't see any of the output of the code. If I were to run these things, I think you would. In fact, let's try it. Yep, there you go. So if I actually ran these, you would get the output of the code. I can do this. There we go. All right. So there you get the output of the code. And I don't remember where my HTML, oh, there's my HTML file. So there you go. And what I like about this kind of format for doing reports, I definitely wouldn't do a scientific paper in this format unless, they're more friendly to stats. But for reports, it's very common for me to use this tool, because then what I have is I have the actual code that I use to do the analysis for the report, and it has the value spit out so that people can go back and they can reproduce this if they had all the information. Like if I was reading in files, if they had the files and they set up the environment the same way, they could reproduce my entire report. And that's what we call reproducible science. It doesn't get much more reproducible than that. So there are going to be occasions where sometimes it will not be 100% reproducible. And that is going to be situations where we have some kind of random number generation going on. And in those particular cases, we can do things like set.seed, which looks, here, let me go down here into the console, set.seed. And then we would put some kind of number in here, like that. And now all the random numbers that are generated by the default R methods have this seed. When we go to run stan, it will require a different seed, its own seed, to be set in order to make everything reproducible. But when you do those kinds of things, then it should become reproducible as well. So that's nice, because now your clients, internal or external, whoever they are, know for a fact that your code does exactly what you said it does. Makes things like auditing a lot easier, which is always good, especially in a highly regulated environment. It also makes sure that all of the plots and everything that are generated from your data are also in the report, and they're generated in real time. So again, overall, it just helps with the reproducibility of everything that we're trying to do. Okay. So I yapped on for a long time. Let's get to the meat of the thing here. So let's pull up on the other side. Okay, it's over there. If I wanted to do a lot of those things that I showed you in the R notebook, I could do them all within this .r file if I wanted to make them into a script. So I could just copy all those so that you don't have to sit here and watch me type. right? I could have all these things in here, right? And I could save this and I could rerun this whenever I wanted to. And it could be a really great thing. Because it's a .r file, I could also run it as a script, and I could say that I could pass in parameters to it from the command line. So I could run it from here, and I could pass in parameters into this script, and then I wouldn't have all these numbers, what we call hard coded in here. So for instance, 0.102 is hard coded in the script. But what I could do is I could say, this is a very useful script that I want to use to calculate posterior probabilities for diagnostic tests. And I want this as part of a pipeline, and that pipeline is going to run in my command line. And rather than having the prior probability of pregnancy being true hard coded in, I could ask for that as a parameter on the command line, or not. Since it's a prior, that might be something that we want to keep hard coded. But definitely the likelihood is something that might change. And so we might have this be a parameter. So these are things to think about, reasons why you might want this in R script. But like I said, I personally would much prefer having it in a report so that I can explain things. I can explain what's going on. I can explain the logic. But just so that I can show you how this works, I highlight it all. I'm going to press, I'm going to press the Control C, and there you can see that the posterior probability that we calculate at the end is 0.92. I'm rounding up a little bit, but because it's in the script, it loses all of its context. You're like, well, but why? Why? How? What does any of this stuff mean? Where'd you get these numbers from? Why is that important? That's why we use this R notebook. So the first part of the R notebook is going to explain what Bayes' rule is. And now I'm going to set up the stats problem that we're interested in. If we wanted to know the probability that someone was pregnant given they had a positive pregnancy test, then our equation is going to look like this. So the posterior probability of pregnant being true, given that the test is true, which means that it's a positive test, equals the probability that the test is true or giving you a positive, given that the person is pregnant, times the prior probability of pregnancy, divided by the prior probability that the test is positive. And again, I'm saying true here. That's the same as positive. And so this next part is just a proportionality. And so it's not uncommon if you read the Bayesian text that we're going to drop off this normalizing factor here, which is the prior probability that the test is positive. Sometimes we just drop that off when we say that the posterior is proportional to the numerator. So you'll see that sometimes too. So as I mentioned here, we can use Bayes' rule to infer the probability that a woman taking this pregnancy test is actually pregnant, given some information. And so how do we do that? That's what this next section talks about. Well, we need certain information. So one of the things that we're going to need to know is, again, what is this prior probability that a woman is pregnant? And so I grabbed some data from 2009 in the United States, which said that 102.1 per 1,000 women were pregnant in 2009. That gives you a pregnancy rate of about 10.2% of women in the United States in 2009. Cool. Again, that is our prior, right? So that is the probability that a woman is pregnant, or that pregnant equals true, as I explain here. So next, what we want to know is the probability that the test will give a positive result. That is, that the test equals true or positive, given the fact that someone is pregnant. Okay, so let's break that down. I want to know what is the probability that the test will be positive given that someone is pregnant. Aha! That given means that we're dealing with conditional probabilities. So I don't necessarily, in this particular question, I'm not looking for the prior probability that the test is positive. I'm looking for the probability the test is positive given that the person taking the test is pregnant. Typically, this is found in the pregnancy test packaging. This is what we would call the sensitivity, the test sensitivity of the true positive rate. For pregnancy tests, they actually have a remarkably high sensitivity. It's quite amazing. Um, in one package that I'm referencing here, it was the sensitivity is 99.9%, which is frankly really good. So that is the probability that the test is positive, given that the woman taking the test is pregnant. All right, so that will be our likelihood. We also need to know the probability that the pregnancy test yields a positive just in general. So that would be both its true positive rate and its false positive rate. In other words, that probability shakes out to be this right here. The probability the test is true or positive equals the probability the test is true or positive given that the woman is pregnant times the prior probability of being pregnant plus the probability that the test is true given that the woman is not pregnant. And I'm not sure I'm going to be able to move this thing over. Oh, there we go. I can do it this way. Times the prior probability that a woman is not pregnant. Okay? That all together gives me the probability that the test is positive in general. All right? So the false positive rate is not always given. However, there's some evidence that it could be as high as 5% when taken later in pregnancy. But for our purposes, um, we would want to know what the real number is, but we're going to assume it's a 1% false positive rate. If we actually knew the real number, we'd get a far better result. One thing that we could do is we could actually represent this as a probability distribution as opposed to just a point probability. That becomes a little bit more advanced for what we're trying to do right now, but that's something to keep in mind. We could do that. So given that the pregnancy rate is approximately 10.2%, the rate of not being pregnant is going to be 1 minus 10.2%, which comes out to 89.8%. So now we're going to code all of this information up, and we're going to code up the Bayes theorem in order to calculate that posterior probability. So what we're going to do is, right here on line 36, we're going to create an object called prior pregnant true. This is the prior probability that a woman is pregnant. And we remember from the information that we got in the story problem that the prior probability is 10.2%. So we put 0.102. In this next part, and by the way, I will strongly suggest that you type all this out by hand because the muscle memory becomes very important, especially if you're going to try to code this, if you're going to try to do any coding in R in the future. So I am not typing this out so that you don't have to suffer and watch me type things, but I do strongly suggest that you type out every one of these parts of the story problem so that you get your hands comfortable with typing out weird things, typing out weird things like these arrows and all these math things. It's very important. There are a lot of people who try to get through computer science courses without coding and just copying and pasting everything, and they turn out not to be the best coders, or at least not the most effective coders, mostly because they just don't have the muscle memory to type really obscure symbols and patterns that commonly pop up. So you're going to have to learn that eventually anyway. You might as well learn it now. So as we said, that was line 36. Line 37 is going to be the prior probability that the pregnant, that they are not pregnant. So that is going to be 1 minus the prior pregnant true. I guess I should mention, you're going to see in R especially, it's very common that we try to use, number one, very descriptive object names to make our code more readable by other people. We try not to use inside jokes in our code because people who aren't in on the joke won't necessarily get it, and then the code will lose some of its meaning. But number three, we try to not use what we call camel case. Camel case looks like humps of a camel. So prior pregnant, true. We avoid typing things like that. We instead, if we have multiple word object names, we're putting underscores in between. Part of the reason why is because, well, you can see it here with this particular font. These capitals do not stand out well. And for some individuals, the camel case can actually make things really hard for them to read and to see. And in my older age, it's definitely harder for me to read that versus the underscores. And so, just for overall readability, we tend to prefer to use underscores. There's some computer languages you may run into. Java is probably the most notorious, where the community prefers camel case. Even when I'm coding in Java, I tend to use the underscores nowadays just because it's easier for me to read, and I have a better appreciation for, after having worked with a large diversity of people, how it can be really hard, especially for people who don't necessarily use English as their primary written language. It becomes really hard to decipher some of these weird camel case things. So underscores tend to work the best. So prior underscore pregnant underscore false is going to be 1 minus the prior pregnant true. And that's because, you know, it's a binary system. So a woman is either pregnant or she's not pregnant. There really isn't this in between state of being pregnant or not pregnant. So you're either pregnant or you're not. So therefore the probability has to add up to 1. You can't have more than 100% of women pregnant or not pregnant. So it's 1 minus the prior pregnant true equals the proportion of women who are not currently pregnant, or who are not pregnant during a particular period of time, or any given time for that matter. The likelihood here is going to be the sensitivity of the assay or the test, because we're curious about, if we go back up here, because we're curious about pregnant being true given the test being positive, then this likelihood is the sensitivity rate. Our sensitivity rate again was 99.9%. So we write likelihood 0.999. The likelihood of the test being true and the pregnancy being false, which is this right here. So the probability of test equals true, pregnant equals false, is 0.01. Again, we got that from the story problem up here, where we know that they could be as high as 5%, but we will assume, for our purposes, a false positive rate of 1%. That's what this object represents right here, is that false positive rate of 1%. So now the probability of the test true, sometimes you'll see, to make this explicitly clear, I might write it a different way, but in this case, just prob is, I might write probability, but I'm not going to in this case. So prob test true, that's how I abbreviate probability. Probability the test is true is the likelihood times prior pregnant true plus the likelihood test true preg false times the prior pregnant false. That's really what we're getting at here. Is, I just lost it. It's gonna be here. We're getting at this value right here, right? So we're just calculating this. So it is this first part plus the second part, and that's really what you see here. So this prob test true is our denominator. So posterior prob here, we're actually doing Bayes' theorem. We've got our numerator, which is our likelihood, times our prior pregnant true, divided by prob test true. And then here, I'm writing print because it's in the report. If I were just down here, if I were running all this in the console, I wouldn't need to write print. So I could just write posterior prob, and it would tell me what it is. But because I'm in the report, generally, just to be safe, some versions of this you had to use print. I don't think you have to use print anymore. I think get away without it. But just to be safe, I still write print because it's ingrained in my head, and that's how I've always done it. And it spits out the number right there. So then we have a posterior probability of 99.9%. What does that actually mean? So now we're getting into the decision analysis stage of the analysis, or the conclusion stage of the analysis. So this posterior probability is 91.9%. What this means is that if you're a woman who's taking this pregnancy test, given the information in this example, there's a 91.9% probability that you're pregnant based on this test. Now, what if we were to change the false positive rate? What if the false positive rate of this test was actually 5%? So we're going from a false positive rate of 1% to a false positive rate of 5%. So how's that change things? Well, here we just changed this to 0.05. Everything else is the same, right? You can see that at a 5% false positive rate, this posterior probability drops dramatically to like 0.69%, or sorry, 69%, right? 69.4%. There we go. That's a pretty big difference, isn't it? Going from 91.9 to 69.4%. That's pretty big. And we only changed the false positive rate by 4%. So what this means is if we have this really low probability, 69 well, comparatively low probability, we're more unsure if the female taking the test is actually pregnant now, right? So we need to think about these probabilities as something more akin to predicting the chances of rain, is how I like to think of it. If you're near a 70% chance of rain, how your behavior changed versus 90% chance of rain. And this isn't uncommon to have a test that does these types of things. What it really shows you is the importance of not only that false positive rate, but ultimately it's showing the importance of that prior probability. That prior probability, if it were much higher, would counteract this 0.05. And you can do that simulation yourself right here with these numbers. You can try it yourself and see how that might change things. Anyway, at the end of the day, we use statistics, especially Bayesian statistics, to make decisions about our world. And, I think I said it before in the very first part of the course. Innately, humans are Bayesians. We have some notion of probabilities, and we have some notion of decisions that we make based on those probabilities. And this kind of shows you a really good example of how the different parts of Bayes' theorem interact in order to create different kinds of probabilities that we might use to change our decisions about things. I think this is really great, and this is really powerful. Anyway, you will have access to this particular file. You can download it, you can play around with it, and you can try things out. The other thing that I want you to do is there's an assignment after this particular lesson that allows you to go through and think a little bit more deeply about Bayes' rule and work through some other examples that are very similar to this one. Work through them, try them out, and if you turn them in, I will grade them, and I will give you if there's no comments to give you, I won't give you any comments. But if I notice that there's something that you might need some help with or something like that, I'll try to give you some comments on that. But try it out, see how it goes. If you want to get a certificate of completion, then I need to see an assignment turned in. If you're just doing this for yaks and you don't really care about getting a certificate, that's cool too. You don't necessarily need to do the assignment, but I strongly encourage you to do it. If for no other reason, it forces you to type. But to me, it's very important that you get this practice, and that you get the practice of actually thinking about how to translate this information in these story problems like this into code like this to get some kind of posterior probability that you can then reflect upon and make some kind of decision about. That's really what this is all about. And ultimately, that is how you're going to learn, and that's how you're going to learn to be a better analyst of any kind, whether you decide to continue with Bayesian stats or if you want to become a frequentist and stick with that, that's cool. But what I want you to ultimately get out of this is a deeper ability to think about what it is you're doing statistically in your analysis. I don't want you to be a robot. I want you to be a thinker. And if you get nothing else out of this course, I hope that's what you get, is the ability to think critically about what it is that you're doing. All right, I've rambled for long enough. Go forth, try that assignment, and good luck. Thank you.